Let's discuss limits at infinity. Limits at infinity and horizontal asymptotes are used to describe the behavior of functions as x assumes arbitrarily large positive values or arbitrarily large negative values. That means that we use limits at infinity also to describe the behavior, the end behavior of the graph of the function. So we use this to evaluate the limit of the function as x approaches positive or negative infinity. The following theorem gives us the limits of power functions at infinity. So if you evaluate a constant over x to the p as x approaches negative infinity or positive infinity, both of these will be equal to 0 regardless of what k is or what the power of p is. So in other words, if you have constant divided by infinity raised to some power, this would always be equal to 0. Now for the limit of a constant times x to the p, this will either be equal to positive infinity or negative infinity, depending on whether you have negative infinity, positive infinity, the sign of k, and whether p is odd or even. So this follows the rule of signs. So when you evaluate this, you take into consideration the sign of your constant, the sign of your infinity, and the value of your p. Now let's use the theorem that we have just discussed to find the limit of this polynomial function as x approaches positive infinity or negative infinity. Now before we proceed, let's take note that whenever you get infinity minus infinity, this is considered indeterminate. Indeterminate means you can't determine it yet at that point, or at that point it is still inconclusive, so therefore you need to do something else. Now to illustrate that, let's take a look at this first polynomial expression here, and let's evaluate the limit as x approaches positive infinity. To evaluate the limit, we just need to plug in infinity to x's here and use the results from the theorem that we just discussed. So here we will have 5 times infinity cube minus 2 times infinity squared minus 3 times infinity plus 6. Now, infinity cube is infinity times 5 is positive infinity. Infinity squared is positive infinity times negative 2. That means minus infinity. And then minus 3 times infinity is negative infinity plus 6. That is just a constant. Now, we can combine these two. You can combine negative infinity minus infinity is minus infinity. In the same way, positive infinity plus infinity is equal to positive infinity. But negative infinity, but if you have positive infinity minus infinity, you can say that that is 0. So same here. I can combine these two, but I cannot combine it with this. So I will only have positive infinity minus infinity. And then you can drop the plus 6 here because that is just a small value compared to infinity. But at this point, you can't tell that this one is 0 because this is indeterminate. That means you can't say that this positive infinity here is the same as this infinity here. So therefore, you can say that this one is equal to 0. So what do you do if you have an indeterminate form? The technique that we can use in this case is to factor out x cubed, or the variable expression with the highest exponent. So in this case, let's factor out x cubed. We have x cubed times, so if I factor out x cubed, that means I would have to divide each term here by x cubed. So 5x cubed divided by x cubed is 5, minus, divide this by x cubed, you have 2 over x. And then here, if you have negative 3x divided by x cubed, you have minus 3 over x squared, plus, and then 6 divided by x cubed is 6 over x cubed. Then you take the limit of the expression here as x approaches infinity. Now, if you recall, when you evaluate an expression constant over x to some power as x approaches negative infinity or positive infinity, this will always give us 0. Or if you plug in infinity to the expression and you get constant over infinity, you get a 0. Now we apply that to the given expression here, because when we evaluate this one using properties of limit is the same as limit of x cubed as x approaches to positive infinity times the limit of the factor here, 5 minus 2 over x plus, or minus 3x minus 3 over x squared plus 6 over x cubed. So we can use properties of limit first. Then here, this one is the first one. This is just equal to infinity. Infinity cube is just infinity times, in this case here, you can distribute the limit to each term. Now here, this one goes to 0 as we've seen from the previous theorem. Constant over infinity is 0. Constant over infinity is 0. This one is also 0 because this will yield to constant over infinity. So each of these will approach to 0. Therefore, we only have 5. So infinity times 5 is equal to infinity. Therefore, we say that the limit of this function here as x approaches infinity is equal to infinity. For the second function, we will evaluate the limit of the function as x approaches negative infinity. And to do that, we will use the theorem that we have just discussed. We will first plug in negative infinity to each of the variable here. So we have 7 times negative infinity to the 4th minus 2 times negative infinity squared plus 3 times negative infinity minus 4. Bear in mind that this follows the rule of signs. So if you have negative infinity to the 4th, that means it will always yield to a positive value. So this gives us positive infinity times 7 is equal to positive infinity. Negative infinity squared is positive infinity times negative 2 is negative infinity. And 3 times negative infinity is negative infinity minus 4. So combining all this, we can combine these two. We can just drop this because this is considered really small compared to the infinities here. So this will result to infinity minus infinity form, which is again indeterminate. Now, if it is indeterminate, then we can't determine it yet at that point. We can't say it's equal to 0. We can't also say it's infinity. We can't combine positive infinity and negative infinity. And the technique that we have learned is to just factor out the highest expression. Factor out x to the fourth. So we will write this as x to the fourth times. So when you factor out x to the fourth, that means you divide each term by x to the fourth. So times 7. That is x to the fourth divided by 7x to the fourth divided by x to the fourth is 7. And negative 2x squared divided by x to the fourth is equal to negative 2 over x squared. And 3x divided by x to the fourth, 3x divided by x to the fourth is 3 over x cubed. And negative 4 divided by x to the fourth is 4 over x to the fourth. You can also check by distributing this to each term, and then you make sure to get back the original expression. So after you factored out the highest expression, the variable with the highest exponent, you then take the limit. The limit as x approaches, in this case, negative infinity. Now, to get the limit here, we will first distribute the limit to each product. So this is the same as evaluating the limit of x to the fourth. X approaches negative infinity times the limit of the other factor, 7 minus 2 over x squared plus 3 over x cubed minus 4 over x to the fourth. X approaches negative infinity. Now from the theorem we've just discussed, limit of this one, negative infinity to the fourth, is equal to positive infinity. In here, when you evaluate the limit, you can distribute it to each term here. You can take the limit of each term. The limit of a constant is constant, so that is just 7 times the limit here. This goes to 0 from the theorem. The limit here is also 0, and the limit here will also be 0. So this is just 7. So that means the limit of the expression here is just equal to 7. Now 7 times infinity is equal to infinity. Therefore, we say that the limit here as x approaches negative infinity is equal to positive infinity. Next, let us consider the following theorem to help us determine the limit of rational functions at infinity. This theorem will also help us identify the equation of the horizontal asymptotes of a rational function. Now, if you are given a rational function of this form, you have your numerator, a polynomial expression, and your denominator, also a polynomial expression, then to find the limit of this expression as x approaches positive infinity or as x approaches negative infinity, all you need to do is just take the leading coefficient of the numerator and the leading coefficient of the denominator and then divide them. So then you will have to simplify the given expression here and identify the limit. Now, note that if the exponent in the numerator or the degree in the numerator is less than the degree in the denominator, so if m is less than n, then when you simplify this, you would just cancel everything in the numerator. So that gives you a constant over b times x to some power here. So if you take the limit of that expression, that will just be equal to 0. Now in that case, the line y equals 0, is a horizontal asymptote of the function. Now, if you evaluate the limit here in this expression for the case when this exponent is equal to the exponent here, or the degree in the numerator is equal to the degree in the denominator, and when you simplify, this will just cancel out. So that cancels out, and that gives you just the constant a sub m over b sub n. So in that case, the limit of the function as x approaches either positive or negative infinity is just equal to the ratio of the coefficients of the leading term of the numerator and the denominator. And then the line y equals the ratio is the horizontal asymptote of the graph. And then lastly, if the degree here is greater than the degree in the denominator, that is m is greater than n, then when we simplify the limit here, we will have some variable raised to some power in the numerator. And the expression here, the variable in the denominator, will cancel out. And then if you evaluate the limit in there, you will either get a positive or a negative infinity depending on the value for your m and your a sub n, b sub n. It follows the rule of signs. So in that case, if you get either a positive or a negative infinity, the graph does not have any horizontal asymptote. Now let's illustrate this by looking at these functions here, and let's evaluate the limit as x approaches positive infinity or negative infinity. So let's consider the limit of the expression here as x approaches positive infinity. Now the technique is to just get the leading term in the numerator and the leading term in the denominator and take the ratio. So when you say leading term, it is the term that contains the highest exponent. And then you take the ratio, you simplify it. As you simplify this, you will cancel x cubed. Okay, using loss of exponents, this one will be simplified as 3x over 4. And then you take the limit as x approaches infinity. Now in this case, you will have 3 times positive infinity over 4. So 3 times positive infinity over 4. Take note that it will follow the rule of signs. So positive times positive is positive. So the numerator is positive infinity over positive 4. That gives you positive infinity. Now, if you take the limit of the same expression as x approaches negative infinity, you do the same thing. You get the leading term in the numerator, 3x to the 4th, and the leading term in the denominator. And then you simplify. You cancel x cubed. You will still end up with 3x over 4. Limit as x approaches negative infinity. This is equal to 3 times negative infinity over 4. Now 3 times negative infinity is negative infinity. Divided by positive 4 is negative infinity. Similarly, when you consider the function here, and then you want to evaluate the limit as x approaches positive infinity, all you need to do is take the leading term in the numerator. So you have 5x cubed. And the leading term in the denominator, the term with the highest exponent, is 4x to the 4th. And then you simplify. So this is equal to When you simplify, you can cancel x cubed. You can cancel x cubed, both in numerator and denominator. So that will be simplified as 5 over 4x. Limit as x approaches infinity. Now we have 5 over 4 times infinity here. 4 times infinity is just infinity. So 5 over infinity, constant over infinity is 0. Now, regardless of whether the denominator is positive or negative infinity, as long as the numerator is constant, this would be equal to 0. Therefore, if you take the limit of that same expression as x approaches negative infinity, you will have 5 over 4 times negative infinity. So 5 over negative infinity is still equal to 0. In this case, we say that the limit here as x approaches either positive or negative infinity is 0. By the way, if this is the case, then we can conclude that y is equal to 0 is a horizontal asymptote. Lastly, let's evaluate the limit of the function here as x approaches positive infinity. And we do that by taking the leading term in the numerator divided by the leading term in the denominator. Now, notice that the degree in the numerator is the same as the degree in the denominator. When we simplify this, we will just get 7 over 3. So the limit of the rational function here as x approaches positive infinity is equal to 7 over 3. And so therefore we say that y equals 7 over 3 is a horizontal asymptote. Now, we have a horizontal asymptote when we evaluate the limit as x approaches either positive or negative infinity, and we get a finite value. So that means if we get 0 or any other value not equal to either positive or negative infinity. And that value, you just have to equate y equal to that value. That will be your horizontal asymptote. And if you get infinity, either plus or minus infinity, therefore you say no horizontal asymptote in that case.